Hi, my name is Shahnawaz. In this lecture, we'll prove one more application of the fundamental group of a circle. Uh, I mean the result which states that pi1 of S1 is isomorphic to Z, and this result is well known by the name Borsuk-Ulam theorem. Now, before we prove this theorem, we will prove some results related to the antipodal maps. Now, what do we mean by antipodal and antipodal maps? So we have this definition. So if X is a point in Sn, where this Sn is a boundary of n plus one dimensional ball, unit ball. So this X is any point in this uh, space. Then it is antipode. So then it is antipode is the point so is a point minus X. For example, if we look at S1, which is the boundary of a two-dimensional ball, so this is over S1. Let us pick any point X in S1. Then it is antipode is a point which is the end point of this diameter. Say this is the point minus X here. Similarly, each point on S1 has the antipode. Similarly, if we take S2, I mean the boundary of a three-dimensional ball. So let us pick any point, suppose here. Now, if this is the point Z, it is antipode will be the point, and this point here, I mean, this is a point minus Z. So again, any point on this ball has the antipode. Now, a map, say H from Sn to Sm is said to be antipodal preserving. Is said to be antipode preserving map if it maps the antipodal pointers to the antipodal pointers. That is if h of minus x is same as minus h of x. Suppose uh, we have two antipodal pointers, say x and minus x. They are antipodes to each other, so they are in the set Sn. So we had to show their image is also antipodal under the antipodal preserving map. So under antipodal preserving map, this has the image h of x. Say that is equal to z, and this has the image h of minus x. Now h being antipodal, so this h of minus x is same as minus times h of x, and h of x is z. So one can note there here that this z and minus z they are antipodes. So hence an antipodal map or antipode preserving map is a map that maps antipodal points to antipodal points. So this is true for all x in Sn. Now we have this theorem here. So if say h from S1 to S1, so if this is a continuous antipode preserving map, then edge is not null homotopy. Then edge is not null homotopy. Let us prove this result. So we had a proof. So let edge from S1 to S1 be a continuous. So be a continuous antibody preserving map. Antibody preserving map. And let B naught be the point 1 0 on the circle S1. Uh, suppose h of B naught is not equal to B naught, then we can define a rotation map. So define, say, row from S1 to S1 to be the rotation map. Such that row maps h of B naught B naught. So what does that mean? So we have S1 here. This is a point B naught. So this is a circle S1, and from S1 to S1 we have the map H. Since this H is not preserved under under this B naught is not preserved under H, so this H may have, this B naught may have image somewhere here under H. Now from this S1, so it's not B naught here, so this B naught gets mapped to this point here. Now from this S1 to S1 we have another map row. Now this is the point so this is the point this is the point H of B naught. Now this row takes this H of B naught back to B naught, so this will be B naught. So this B naught is same as a row of H of B naught. Now this H takes this B naught here, and this row takes this H of B naught back to its original position. So one can note here that this row being a rotational map, I mean the rotation map, so it is clearly antibrittle map, because if these 2 points are antibodies and row is the rotation map, suppose this row is the rotation by an angle theta, so this point B gets mapped to this point, and this point here, this gets mapped to this point. So if they were the antibrittle points, then they are clearly the antibrittle points, because this angle is equal to this angle. So Now one can note here, now rho being the rotation map, rho is clearly antipode preserving. Rho is clearly antipode preserving. Also, H is given to be antipode preserving, hence their composition is antipode preserving. Hence, the composition rho composed with H is antipode preserving. Now, if this H is homotropic to the constant map by the homotopy H, so now if H is homotopic to the constant map via the homotopy, say H, then this rho composite H is again is also homotopic to the constant map via the homotopy where the homotopy rho composite H. That means this homotopy implies this homotopy. So if these two maps are not homotopic, so these two maps cannot be homotopic. So we are using here the contrapositive statement. Here A implies B means not B implies not A. So if these two maps are homotopic, then these two maps are homotopic. In other words, if these two maps are not homotopic, then this cannot be, these two maps cannot be homotopic. In other words, H cannot be non-homotopic. So hence, if rho H is not null homotopic, then H is not null homotopic. Now, the special thing about this rho H is that it preserves B naught, i.e., rho of H of B naught is same as B naught. So therefore, it suffices to prove the result under the additional hypothesis that this H preserves B naught, because that won't make any difference. So therefore, it suffices to prove the result under the additional hypothesis that H of B naught is B naught, because if they are not equal, then we have this rotation map such that if rotation map is not non-homotopic, this is not non-homotopic. So we can assume H of B naught is B naught. Now we have the step first. While so in step first we define a map. So define a map, say Q from S1 to S1 by Q of Z is Z square for all Z in the complex plane. Or in the real coordinates, uh, Q of cos theta sin theta is cos of 2 theta sin 2 theta. Now one can note here this Q is continuous, this is closed, and this is surjective. Hence this is a quotient map. So note that Q is continuous, closed, and surjective. So hence Q is the quotient map. Now Q being quotient map, so here we have this diagram. So this is S1 here, and from S1 to S1 we have the map H. From S1 to S1 we have the map Q. Again here we have the map Q. Now this Q being quotient, so this composition Q composite H will induce a map from S1 to S1. So let us call that K, such that this diagram commutes. Mm. So this diagram commutes. So now Q being the quotient map, mm, so Q will induce, so the map Q composite H induces a map K from S1 to S1 such that Q composite H is same as K composite Q. Note that if we substitute Q of B naught, i.e. Q of 1 0 here in this map, then we get the map we get the point 1 0 back. So note that Q of B naught is same as B naught, and this B naught is same as H of B naught, because this is what we have assumed in the hypothesis, and hence K composite H of K composite Q of B naught is same as, since these two maps are equal, so this is Q of H composite B naught, or let us write it this way. So or K of B naught, because Q of B naught is B naught, is same as Q of B naught, and Q of B naught is same as B naught. So that means K maps the point B naught to B naught. Now in step second, we prove the map K star is non-trivial, where K star is a map induced by this K. So since K from S1 to S1 is continuous, we have the induced map K star from the fundamental group of S1 based at B naught to the fundamental group of S1 based at B naught. So we'll prove K star is non-trivial. So we will prove K star is non-trivial. So one can note that the map Q, so note that uh, the map Q from S1 to S1, so this is a covering map. So one has to verify this. So this is lab 10 exercise. So this is the covering map. The proof of this is similar to the proof that the standard map say uh, I mean to prove this Q is a covering map. So its proof is similar to prove the standard map P from R to S1 is a covering map. So if for instance U is any subset, so we have this circle here and this is this circle here and we have this map Q here. So if U is the subset of S1 consisting of those points having a positive second coordinate, I mean this set here, so this is S1 here, this is S1 here, so I'm taking this open arc here. So this is the set of those points in S1 which have the positive second coordinate here. Then let us call this U. Then P inverse U will be the set of I mean P inverse U consists of those points of S1 lying in the first and third quadrant. I mean P inverse U will be these two open arcs. So similar arguments apply when U is the intersection of S1 with the open lower half plane or with the open right and left half planes. So this is a trivial exercise to prove. I mean showing the map Q here is the covering map. So here we have S1, we have the map Q here from S1 to S1, and this is the interval 0 1. So now if f tilde from the interval 0 1 to S1 be a path from B naught to B minus B, I mean be a path from B naught to minus B. So if this is a circle here, so this is a path from this point to this point, I mean this f tilde starts at B naught and ends at minus B. And let f be the composition of, so this is a map f tilde, and this f is the composition of q and f tilde. So this is a map from the interval 0 1 to s1. So this is the map q composite f tilde. So then this f is a loop. So then f of 0 will be q of f tilde of 0. Now since this f tilde of f tilde starts at b, so f tilde 0 will be q of uh, naught. So this is b naught and minus b naught. So this is q of b naught. But q of b naught is same as b naught, and f of 1 is q of f tilde of 1, and f tilde of 1 is same as minus b naught, because f tilde ends at minus b naught. So this is q of minus b naught. But q being the square map, I mean q maps z to z square, so q of minus b naught is same as q of b naught, and q of b naught is b naught. So this means that this f is a loop in s1. So therefore f is a loop in s1 based at b naught. Hence the homotopy class of f uh, is an element of, and hence the homotopy class of f is an element of the fundamental group of s1 based at b naught. Now finally we prove that k star is non-trivial. So finally we show that k star is non-trivial. Let us move to the next page. So finally we show that k star is non-trivial. So we have, so if we look at this image of this homotopy class under k star, this will be the homotopy class of k composed with f, but f is same as q composite f tilde. So this is same as by associativity, this is same as k composite q composite f tilde, but k composite q is same as I mean it's the same as q composite h. So this will be the homotopy class of q composite h composite f tilde, and this will be by associativity, this will be the homotopy class of q composite h of f tilde, and this is q star of the homotopy class of h of f tilde. And now in so this is where this h of f tilde is, where h of f tilde is a map from interval 0 1 to s1 such that h of f tilde of 0 is b naught. I mean this is h of b naught, which is b naught, and mm, h of f tilde of 1 is h of minus b naught. Now h being the antibody preserving, so this is minus times h of b naught, which is minus b naught. So this element over here, this is a path starting at b naught and ending at minus b naught. Now uh, this q star, this corresponds to the multiplication map by 2. I mean, we have uh, pi 1 s1 b naught to pi 1 s1 b naught, and here we have the map q star, where q star takes the homotopy class f to q composite f, and here we have the isomorphism with z, and this is the isomorphism with z. So uh, this so the map which takes uh, I mean the map q which takes the element z to z square corresponds to the map which takes if uh, I mean if f corresponds to the element 1 here, then q of f corresponds to element 2 here. So this corresponds to the map, I mean the multiplication map by 2. So this uh, q star over here, this is non-trivial. I mean this is injective. So now this map q star being non-trivial implies this k star is non-trivial. So so that is since we proved that this edge of f tilde is a path starting at b naught and ending at minus b, so that is edge composite uh, f tilde is a path in s1 from b naught to minus b naught. So hence this homotopy class of edge of f tilde, so, so here we prove this k star map is the element this f to the element q star of f. Now q star being non-trivial, so q star of this element is non-trivial, so k star of this element is non-trivial. So hence this homotopy class of f uh, which is an element of the fundamental group of s1 based at b naught, so this is a non-trivial element, so it's a non-trivial element. And since q star from the fundamental group of s1 based at b naught to fundamental group of s1 based at v naught uh, is I mean corresponds to the multiplication map, so this corresponds to the multiplication by 2 in z, which is isomorphic to pi 1 s1 b naught. So hence this q star is injective, and q star being injective and this edge composite f tilde being non-trivial element, so this is a non-trivial element. So that means k star map is this non-trivial element or non-trivial element. This means k star cannot be null homotopy, otherwise k star maps this element to the constant to the trivial element. So hence which is the element 0 in z. So hence k star is mm, non-trivial, is a non-trivial map. Now in step third, we finally prove and that H star is not null homotopic. So this is the step third. So finally we prove that. Finally we prove that H star is non-trivial. Now showing H star is non-trivial means H is not null homotopic. So that H is so that H cannot be null homotopic. Now since K star is non-trivial, and K star um, being a group homomorphism from an infinite cyclic group with itself implies it is injective. So since K star is non-trivial, it is therefore injective. It is therefore injective because being group homomorphism from an infinite cyclic group with itself. Also, this Q star corresponds to the multiplication by 2. So also Q star corresponds to, to multiplication by 2 in pi 1 S1 B naught. So Q star is injective, K star is injective. It implies that hence Q star is injective. Therefore, I mean, since Q composition H, this composite map is K composite Q, we have, so since these two are equal, so therefore Q star composite H star is same as K star composite Q star. So K star is injective, Q star is injective, so this implies this composition map is injective, hence this is injective. Now this being injective means H star is injective because Q star is injective. So since these two are equal, Q star composite with H star is K star composite Q star. So since K star composition Q star is injective, hence H star is injective. Now H star being injective means H cannot be null homotopic. For if H is null homotopic, then the homotopy class of, I mean, then the map induced by H star H will be the trivial map. So hence H is not null homotopic. So one can note here, if H is null homotopic, then the map induced by H, which is H star, will be a trivial map, and hence H star cannot be injective. So this proves the theorem. Now we have one more theorem which states that there is no continuous and brittle map from S2 to S1. So there is no continuous, there is no continuous anti um, antibody preserving map G from S2 to S1. So let us prove this. So assume on contrary. So assume that uh, there is a continuous map. There is a continuous antipodal preserving G from S2 to S1. So let us take S1 to be the equator of S2. So let S1 be the equator of S2. So what is our assumption here? It is, so we have S2 here. We assume there's a map which is continuous and antipodal G. Now this is the equator of S2 and this is equal to S1. So this is now uh, we can restrict. So then the restriction map H, which is the restriction of G from to S1. So we restrict to this G from S2 to S1. So this is a map from S1 to S1. So this is a continuous antipodal preserving map. So this is a continuous antipodal preserving map. So that means H cannot be null homotopic. So hence H cannot be null homotopic. But on the upper hemisphere U of S2 is homeomorphic to the ball B2. So if we take this upper hemisphere of S2, so but upper hemisphere, let us call this U of S2 is homeomorphic to the ball B2. Now one can note here we can extend H continuously to U. So since we can extend G, since we can extend H continuously to U, therefore uh, this this edge is null homotopic. Therefore, edge is null homotopic. So one can note here we have this map H defined on this S1, and this H is nothing but the uh, restriction of the map G from S2 to S1 to the equator, which is in this case the circle. So therefore H is null homotopic. But um, but this G is continuous extension of H to E, hence G is null homotopic. So but G is uh, the continuous extension of H to U. Hence, this hence G is null homotopic, which is not the case because G cannot be null homotopic because any continuous antipodal to the map is never null homotopic. So, hence, there is no continuous map from uh, S2 to S1, which is continuous and antipodal preserving. So finally, we have the Borsuk Plum theorem. So it states that given a continuous map, given a continuous map f from S2 to R2, there is a point x such that it is antipode is mapped. I mean such that the x and it is antipode minus x are mapped to the same point. So that means if we have S2, I mean if we have S2 and we project this S2 down to the plane, then there will always be two. I mean, there will always be a pair of antibodies which are mapped to the same point in R2. This is what this theorem states. Suppose, so this is the proof. Suppose this is true for all. Um, I mean, this is so. Suppose f of x is not equal to f of minus x for all x in uh, S2. So we assume that there are no pair of antibodies which are mapped to the same point. So then the map g of x, which is f of x minus f of minus x divided by the length of this vector. So this is continuous map. This is continuous map. Also, g of minus x is same as, so if we put here so this is same as f of minus x minus f of x divided by norm of f of x minus norm of f of minus x. I mean, g of minus x will be same as minus of gx. So i.e. g is antipode preserving map. So we then proved. So now, so then G, so i.e. this G is a map from S2 to S1 because the length of this uh, vector over here is 1. So this point will lie on S1. So this is antipode preserving map. But we just proved there is no such map which is continuous and antipode preserving. So this is a contradiction. Hence, there exists x in S2 such that f of x is same as f of minus x. So this is Borsuk theorem for S2. So it has generalization to Sm for any positive integer m.